Okay then, good. Let's start section 12.3, the dot product. So the dot product, sometimes called the inner product, the scalar product, is defined as just the sum of the products of the individual components of the vectors that we're dotting together. So suppose that A is a 3 vector with components A1, A2, A3, and B is a 3 vector with components B1, B2, B3. Then A dot B is defined as A1 times B1 plus A2 times B2 plus A3 times B3. And of course, for a 2 vector, a 4 vector, a 5 vector, a 6 vector, etc., it's defined the same way, analogously. So let me give you some idea about differing notations for the inner product. So in mathematics, we usually use the following notation. So rather than this dot, we usually use a parentheses to denote the inner product. Not a great notation since other things are denoted by that, but in physics, well, first off, usually a vector is denoted by this bracket in this little bar. So this is called a bra. And then the dot product, well, the other thing is called a cat. The bar with a B and then the little bracket there. So A dot B, the inner product, is defined as this, which is called a bra cat. So here's the bra and this is the cat. Okay, so let me give you some properties of the inner product. Actually, anything that satisfies these properties will be called an inner product. Okay, good. Well, forget that. Oh, I got it, erased it. Good. Okay, so suppose A is a vector, meaning A is a member of a vector space, and B is a vector, a member of a vector space, and C is a vector. And let D be a scalar, so a member of some field, the scalar field. Then, if these vectors and scalars satisfy the following properties, we say it's an inner product. Or, of course, well, the dot product will satisfy these. So, A dot A is always greater than or equal to 0. And in fact, A dot A is 0 if and only if A is the 0 vector. So the dot product of a vector with itself will be greater than 0 unless unless you're doing the dot product of 0 with itself, the 0 vector with itself. In which case, the dot product of the 0 vector dotted with the 0 vector is the number 0. Okay, so the dot product, the inner product, is commutative. Well, actually, it's commutative except for this one little technical detail. So A dot B is equal to the complex conjugate of B dot A. So if I'm just talking about real numbers, then the dot product will be commutative. If I am talking about, well, that these are complex numbers, then it's not quite commutative. When you switch the order, you just get the complex conjugate of your answer. Next, I have that the dot product distributes over vector addition. So the vector A plus the vector B dotted with the vector C is just the dot product of the vectors A and C plus the dot product of the vectors B and C. And lastly, if I have a scalar d times a dotted with b, then that's the same as the scalar product d time. Well, actually, no, this is actually not a scalar product. It's just a product within the scalar field. D times the vector a dot the vector b. So note the following. A dot a, we'll denote that by the norm of a squared. And so we can define a norm on a vector space which has an inner product by just defining the norm as being, well, the norm squared of the vector is just being the dot product, the inner product. Note that 0 vector dot any vector is equal to 0. So let me give you some further terminology. An inner product space. A vector space with an inner product is called an inner product space. A Hilbert space. So a very special type of inner product space will be a Hilbert space. So basically a complete inner product space is called a Hilbert space. So if every series of vectors which converge absolutely implies that series converges, then we say that this inner product space is complete and we call it a Hilbert space. So if you have a vector space and you attach to it an inner product, and then that if that inner product is complete, then if the vector space is complete under that inner product, then we say that this is a Hilbert space. The angle between two vectors. So a dot b is the norm of a times the norm of b times cosine of theta. Okay, so I want to show that. So that this be the vector a, this be the vector b, and this be the vector a minus b, since the sum of b and a minus b is a. So then I have the following. The norm of a minus b squared by the, well, it's a extension of the Pythagorean theorem. It's the law of cosines. So by the law of cosines, the square of this length is equal to the sum of the squares of these two lengths. So the norm of a squared plus the norm of b squared minus 2 times the length of a times the length of b times cosine theta. So this is the law of cosines. Okay, so well, I have that a minus b is just by the above, the length of a vector is just, I can define it as a the square root of the inner product, and so this is just the inner product of a minus b with a minus b. So let's multiply this out. And so this is just A dot A minus A dot B minus B dot A. Minus and minus make that a plus B dot B. And so this is equal to, well, this first term is just the norm of A squared. The second term, well, actually, let's do it the other way. This last term is the length of B squared. And assuming that I'm talking about real numbers, then A dot B is the same as B dot A. And so this is equal to minus 2A dot B. So, since these are equal, well, this is equal, so therefore these are equal. And so I have that A dot B is equal to, dividing by 2, the length of A times the length of B times cosine theta. And that's what I wanted to show. Okay. So, as a corollary, well, you can just divide by the length of A and the length of B, assuming that neither A or B is 0, and get that the cosine of theta is A dot B over the length of A times the length of B. So I can define the angle between two vectors, A and B, as that vector such that the cosine of theta is equal to this ratio. Orthogonal vectors, perpendicular vectors. So, since I can define the angle, well, two vectors can be thought of as being perpendicular if the angle between them is pi over 2, 90 degrees. Then cosine of pi over 2 is 0. And so that says that this ratio is 0. And so the numerator must be 0. So knowing that, I will now make a definition. A and B, vectors A and B, are called orthogonal vectors if their inner product is 0. And so if the inner product of two vectors is 0, I say that they are orthogonal. The direction cosines and the direction angles. So let A be a 3 vector with components A1, A2, A3. Then the unit vector, well, that's just the A divided by the length of A, will have a unit length. Therefore, it's the sum of the squares are going to be 1. So because of that, I can define the numbers here to be cosine of some angles. So I'll call it cosine of alpha, cosine of beta, cosine of gamma. And so cosine of alpha is just A1 over the norm of A. Cosine of beta is just A2 over the norm of A. And cosine of gamma is just A3 over the norm of A. So these are my direction cosines. And alpha, beta, and gamma are the direction angles. Projection. So, this is an orthogonal projection. So suppose I have some vector A and some vector B, and I want to project the vector B onto the vector A. So, and I want to do it orthogonally. So I can just sort of project this down. The scalar projection will just be the length of this. And so the scalar projection of B onto the vector A, the component of B along A, so this component here of B along A, so this length here, is defined as, well, you can see this is just, and it's denoted by COMP, and then subscript is A, and then of B. So this is the component of B along the vector A. It's just A dot B over the norm of A. So my vector projection, so this vector projection here, will be a vector having the length of the component of B along A in the same direction as A. And so if I just multiply the component of B along A by the unit vector in the direction of A, meaning A over the norm of A, I then get, well, A dot B over the norm of A squared times A. The norm of A squared is just A dot A. And so the vector projection of B onto A, denoted by the projection of B on the vector B onto the vector A, is just A dot B over A dot A times the vector A. By the way, of course, we're always assuming that the vector A is not 0. So we're assuming A is not 0, of course. Maybe I should actually say that. So suppose it's not the vector A. It's not the 0 vector. Okay. Okay, so let's see if I can make that red. Okay, good. The orthogonal projection. And so this was the vector B. Here is its projection. Oh, and maybe I should write the orthogonal projection here. Maybe, oh, in purple. Yeah, let's do it purple. Okay, so this is the orthogonal projection of B onto A. And so the orthogonal projection of B to A, denoted by orthogonal projection of B to A, is just B minus the projection of B onto A. So let's do some examples. On page 852. In exercises 2 through 10, find the dot product of A dot B. So let's find A dot B. So A dot B for the vectors 4, 1, 1/4, and the vector 6, -3, -8 will be, okay, come on, thank you. It'll be 4 times 6 plus 1 times -3 plus 1/4 times -8. So that's equal to 24 minus 3 minus 2, which is 19. And so the dot product of those two vectors is 19. Okay, let's determine the dot product of these two vectors, given that its length is 80. The length of A is 80. The length of B is 50, and the angle between A and B is 3 pi over 4. Well, recall that A dot B is the norm of A times the norm of B times cosine of theta. And so this is equal to 80 times 50 times cosine of 3 pi over 4. And so 80 times 50 is 4,000. Cosine 3 pi over 4, well, let's see. Cosine pi over 4 is 1 over rad 2. And so cosine of 3 pi over 4 is a negative, and let's rationalize the denominator, rad 2 over 2. And so I get a negative 2,000 rad 2. And that's the dot product. Note the dot product is not necessarily positive or negative. It's just that A dot the vector A dot the vector A will always be greater than or equal to 0. Let's do problem number. So in exercises 29 through 30, find the acute angles between the lines. Okay. And so on problem 29, I have the line 2x minus y equals 3 and the line 3x plus y equals 7. So let me pick, I guess I'll do it this way. Let me pick 2 points on the line 2x minus y equals 3. So I can do 1 minus 1. That's one solution. And let's say 0 minus 3. Okay. So then A would be 1 and subtract, so you get a 2. Okay. And so that's your first vector, A. Let's do, I can do 2 points. I can also just do a slope. And so let's do 2 points on 3x plus y equals 7. So you can do 2, 1. 6 plus 1 is 7. And you can do 0, 7. Okay, so then B is, well, 2 and 1 minus 7 is a minus 6. Okay. So let's do this. Find the angle. Okay. So let's find the length of A. So that's just going to, well, let's do length squared. So that's going to be 1 squared plus 2 squared. So that's going to be 5. And so the length of A is rad 5. Let's do B. So the length of B squared is 2 squared plus minus 6 squared. And so that's 36 plus 4 is 40. And so, oops, there any way I can get rid of this guy? Good. Okay, let's see what happened. There it is. Okay, so the length of B okay, good. The length of the vector B is going to be 4 times 10, so it'll be 2 rad 10. Okay, so let's do A dot B. Okay, good. Got rid of that. So let's do A dot B. So this is going to be A is 1. So it's 1 times 2 plus 2 times negative 6. Yes, it is 1, 2, and 2 negative 6. So this is equal to 2 minus 12, which is a negative 10. Okay, so now noting that A dot B is equal to the length of A, norm of A times norm of B times cosine theta. And so I get negative 10 is equal to rad 5, 2 rad 10 cosine theta. Okay. So that's going to be 50, so that's 5, that's 10. Rad 2 cosine theta is negative 10. So divide both sides of your equation by 10 rad 2. So I get the cosine of theta. Get rid of that. If I can. Come on. Okay. A little bit of frozenness here. Okay, good, good. Okay, so I have cosine theta is equal to a negative 1 over rad 2. So theta is 3 pi over 4. Okay, so that's the angle between those two vectors. But they ask us for the acute angle. And so let's then, let's look at the acute angle. So rather than that one, they want the pi over 4. So they want pi over 4. So theta is pi over 4, and that's your acute angle. Okay, so let's do in exercises 31 through 32. Find the acute angles between the curves at their points of intersection. The angle between two of their tangent lines at the point of intersection. Okay, so I have here y equal x squared and y equal x cubed. So let's first find the point of intersection. So I'm going to set x squared equal to x cubed. And so I have x cubed minus x squared is 0. So x squared times x minus 1 is 0. So x is 0 or x is equal to 1 by the zero factor property. And I don't really care that that's a double root. Okay, so let's take derivatives. So y prime equals 2x or y prime equals 3x squared. Yes. Okay, good. So let's see what happens at 0. Well, I have here that the derivative is 0. Similarly, well, and so the vector A, well, I can say that since it has a slope of 0, I can go 1 in the x direction and 0 in the y direction. So that's one angle. Okay, and now let's do this again at x equals 0. So again, y prime is 0. So I can let b also be 1, 0. Okay, and so the length of the norm of a squared is just 1 squared plus 0 squared. And so this is a unit vector. Similarly, the norm of b squared is 1 squared plus 0 squared. So the norm of b is 1. Okay, so since a dot b is the same as the norm of a times the norm of b times cosine theta, we have, well, a dot b, well, we can compute that. I guess I should compute a dot b first. Actually, let me do that first. So this is 1, 0 dot 1, 0, which is 1 squared plus 0 squared, which is 1. So now, since a dot b is the norm of a times the norm of b times cosine theta, then, well, 1 is equal to 1 times 1 times cosine theta. Therefore, cosine of theta is 1. And so if I want to find an acute angle, then theta is 0. Come on. Stop. Okay, good. So this is an acute angle. Okay. Now let's do this at, what was the other one? 1. Okay, so I did this when x is 0. Let's do this when x is 1. So at x equaling 1, at x equaling 1, so this was 2x, and the other was 3x squared. So a 2 and a 3. Okay, so I have a little dash there. I wonder if I should put, well, that's obvious for that. Okay, I'll just leave it like that. Okay, so the slope is 2. So I can go 2 in the x, 2 in the y, and 1 in the x. Okay, and for b, I can go 1 in the x and 3 in the y. Okay, so I have that the length, the norm of a squared, is 1 squared plus 2 squared equals 5. Why isn't that squared? Oh, I hope I wrote squared up here also. Yes, I did. Okay, good. Just checking. Therefore, the norm of a is rad 5. The norm of b is 1 squared plus 3 squared, so that's a 9, a 10. So the norm of b is equal to rad 10. Okay, let's determine a dot b. So a stuck again. Okay, now it's moving. So a dot b is equal to 1 plus 2 times 3 is 7. Okay. Well, recall that a dot b is the norm of a times the norm of b times cosine theta. So 7 is equal to rad 5, rad 10, cosine theta. And so 7 is equal to 5 rad 2 cosine theta. So cosine theta is equal to 7 over 5 rad 2. So theta equals arc cosine of, let's multiply and divide by rad 2, I guess. 7 rad 2 over 10. And that is your answer. Okay. Okay, so let's do problem 35. In exercises 33 through 37, find the direction angles, the direction cosines, and the direction angles of the vector. Give the direction angles correct to the nearest degree. Okay. So let this be the vector A. So then the norm of A squared is 1 squared plus minus 2 squared plus minus 3 squared, which is 10, 14. And so the norm of A is rad 14. Okay, good. So the cosine of alpha is equal to 1 over 14. So 1 over rad 14. I guess I'll leave it like that. The cosine of beta is negative 2 over rad 14. And the cosine of gamma is negative 3 over rad 14. Okay. So the angles are, well, alpha equals arc cosine of 1 over rad 14 beta arc cosine of negative 2 over rad 14 and gamma equals arc cosine of negative 3 over rad 14. So these are my direction angles, and these are my direction cosines. In exercises 39 through 44, find the scalar and vector projections of B onto A. Okay, so let's do that. So first, let's determine the dot product of A and B. So A dot B is 4 times 3 plus 7 times negative 1 plus negative 4 times 1, which is 12 minus 7 minus 4, which is 1. Oh, yeah. And so let's determine the magnitude of A and the magnitude of B. So the norm of A squared is 4 squared plus 7 squared plus negative 4 squared, 16 plus 49 plus 16. That's 50, 65, 75, 81. So 81. will you stop? Okay, good. So 81. So the length of A, the norm of A is 9. Okay, so I have that the component of of B along A and maybe I should skip a line. Well, that's just equal to, from the above, A dot B over the length of A. So this is equal to, well, let's see, A dot B was 1, and the magnitude of the norm of A was 9. Okay. I think that was one of the questions that was asked, was to find the scalar. Okay. So now let's find the vector projection. So the projection, actually maybe I should do this. Whoa. Thank you. Okay, so finally, okay, what is going on? Okay, so next, the projection of B onto the vector A is just A dot B over, maybe I'll write it this way, the magnitude of A squared times the vector A. And so this will equal, so the projection of the vector B along the vector A is A dot B, which was 1, over the norm of A squared, which was 81, times the vector A. Okay, times the vector A. And the vector A was 4, 7, negative 4. So let's write this as 4, the vector 4 over 81, 7 over 81, negative 4 over 81. And that is your answer. Problem number 45. Show that the vector, the orthogonal projection of B onto A, which is equal to B minus the projection of B onto A, is orthogonal to A. It is called the orthogonal projection of B. So I want to show that if I take the dot product of the vector A with this other vector, that then I will get 0. So I want to show that this will be 0. So this is equal to A dot, well, this is B minus the projection of B onto A. And so I have A dot B minus, well, this projection here is just A dot B over A dot A times A. And so let's multiply this inside. So this is equal to A dot B minus, well, this first quantity here is just a scalar. So I can just bring it out in front. Times, well, A dot A. Well, the A dot A's cancel. So I just get A dot B minus A dot B, which is 0. And that's what you wanted to show. Okay. And maybe I'll say start here and end there. Problem 53. Use a scalar projection to show that the distance from the point P1, x1, 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 y1 to the line ax plus by plus c equals 0 is the absolute value of ax1 plus by1 plus c divided by the square root of a squared plus b squared. Use this formula to find the distance from the point negative 2, 3 to the line 3x minus 4y plus 5 equals 0. Okay, so let's do that. So first, let's say P0, x0, y0, be a point on the line. Ax plus by plus c equaling 0. And suppose it's not the same point. So suppose P0 is not P1. Okay, not sure if I need that or not, but I probably will. So now I have that, well, since it's a point on the line, it satisfies the equation of your line. Okay. And so I have that C is equal to negative ax0 minus bx0. So C is equal to a negative ax0 minus by0. Also, we have the following. Since ax plus by plus c is 0, we have that by is equal to minus ax minus c. Therefore, y is equal to minus a over b minus c over b. Assuming b is not 0. Okay. So, let the vector u be the vector, let's say, minus b, a. So I'll go a in the y and minus b in the x. Doesn't really matter, they put the minus at the bottom, but in you know, for the x. So this is a vector in the same direction as the line ax plus by plus c equaling 0. Okay, or opposite. So it's along a line, so it's, you know, obviously you either go in one direction along the line or or the opposite direction along the same line. And so an orthogonal vector to it will be AB. So AB, V is a vector orthogonal to the line ax plus by plus c equaling 0. Okay. So w, the vector w, let this just be x1, the vector going from p0 to p1. So x1 minus x0, y1 minus y0. So this is a vector from p0 to p1. So the distance from P1 to the line AX plus BY plus C equaling 0 is just going to equal the length of the component of W projected onto V, but of course it could be a negative, so let's put an absolute value. So this is equal to V dot W over the length of V, the norm of V here, and we'll have to put an absolute value. So I should note that V dot W is, well, let's see. So I have V, it's just AB dot W, which is x1, y1 minus y0. And so I have that V dot W is A x1 minus x0 plus b y1 minus y0. And so this is just ax1 plus by1 minus ax0 minus by0. Okay. And from this, oh maybe, yeah, so from this, I have that this is equal to ax1 plus by1 plus, well, this term here is just c from the above. Also, the norm of v squared is just going to be a squared plus b squared. And so the length of v is radical a squared plus b squared. And so let's look at this. So the distance d to the line is just the component of w in the direction of v, which we've shown is equal to a x1 plus by1 plus c over the square root of a squared plus b squared. Good. And that's what we wanted to show as far as that first part. And now let's do a computation. Okay. So now let's use this formula to find the distance from the point negative 2, 3 to the 1 to, there it is, to the line. Okay, good. So the distance here is just, so I have 3, negative 4, 5. So that's the line. And a squared plus b squared is, well, 3 squared plus 4 squared. And it's at the point negative 2, 3. Okay, so d is equal to negative 6 minus 12 plus 5 over the square root of 16 plus, so 25. So that's equal to, it's going to be a 5. The absolute value of, that's negative 18, so 13 over 5. So the distance is 13 over 5. So the distance from the point negative 2, 3 to the line 3x minus 4y plus 5 equaling 0 is 13 over 5. Let's do, lastly, so this is the very last problem, use theorem 3 to prove the Cauchy-Schwartz inequality. A dot B is less than or equal to norm A, norm B. So let's prove this. So A dot B is equal to norm A, norm B, cosine theta. Okay, so the absolute value of A dot B therefore is equal to the norm of A, norm of B, times the absolute value of cosine of theta. Well, cosine of theta is always less than or equal to 1, so this is less than or equal to norm A times norm B. So I'm done. Let me do a better proof. So this is true, but it's really using really the fact that we use the law of cosines is really more or less it's sort of circular, that we're proving Cauchy-Schwartz and using the law of cosine. So let me do a better sort of proof here that's sort of independent of the law of cosines and really a circular sort of argument. So first off, if A were 0, then the dot product with any vector would be 0. And in addition to that, obviously the norm of A would be 0. And so trivially, we would have that 0 is less than or equal to 0. Okay, so let's assume that A is not 0. So if A is not the 0 vector, then I have the following. Let's look at R A plus B dot R A plus B. Well, I know that this is non-negative because any vector dot product with itself is always greater than 0, and it's 0 if and only if this whole thing is 0, but that can't be true. Okay, so let's multiply this out. So I have R squared A dot A plus R A dot B plus R B dot A plus B dot B. Okay. And so this is just R squared. Well, maybe I'll write it this way. The norm of A squared, R squared, plus, I can assume that I'm only talking about a real inner product, a real dot product. So I'll change the order here. It's commutative. So this is 2A dot B R plus norm of B squared. Well, if I look here, the left-hand side is quadratic. So this, well, the right-hand side, I will say, is quadratic, in R. And since the leading or the coefficient of R squared is greater than 0, that means it goes up. And so that means that, well, you can't have two unequal real roots. So this can't have two unequal real roots. So this implies that the discriminant is less than or equal to 0. And so, just looking at the discriminant here, so I have that b, so that's 2a dot b minus 4a b, c, which is the norm of b squared. This must be less than or equal to 0. Okay? And so I have 4a dot b what in the world? Okay, 1 second. There it is. I'm back. A dot b squared minus 4a squared norm of b squared. Okay, so let's bring the norm of a squared times the norm of b squared to the right hand side of the inequality. Well, divide by 4 first. And so a dot b squared is greater than or equal to a squared norm of b squared. But since the square for non-negative quantities is always increasing monotonically, then this is greater than or equal to norm of a times norm of b, and that's what you wanted to show. Okay, so 2 more minutes. Let me prove the very last thing. Okay, good. The parallelogram law states that the square of the norm of a plus b plus the square of the norm of a minus b is equal to 2 times the square of the norm of a plus 2 times the square of the norm of b. So prove the parallelogram law. Okay, so let's do that. So it says, hint, use exercise 62. Okay, good. Okay, so let's do this. Come on. Come back. Thank you very much. Okay, so let's do this. So I have the square, the norm of a plus b plus the square of the norm of a minus b. So this is equal to a plus b dot a plus b. The second one is a minus b dot a minus b. So let's multiply this out. So this is a dot a plus a dot b plus b dot a plus b dot b. And now for the second one, it's a dot a minus a dot b minus b dot a, minus and minus make it a plus, b dot b. These cancel, these cancel. So you have two of these, so this is equal to 2 norm of a squared. A dot a is just the norm of a squared, plus, and you have two of these, so 2 norm of b squared. And that's what you wanted to show. And so that is it. So let me end this. Stop recording. Stop recording.